Okay, good morning, all of you. So today we'll be seeing how a finite series is convolved with infinite series. Okay, so when you have a finite series and an infinite series, how do you proceed with um, convolving them? Linear? How do you linearly convolve them? Linearly convolve them. So for that, okay. Suppose you have a finite series, um, 2, 1, 2, 1. Let us call this Hn, and let us call this another series Xn, which is an infinite series, or it's a series of very large length compared to Hn. So Hn has a very large support, Xn. To do the convolution of these two series, we have two methods um, called overlap add method and overlap save method. These are the two methods. Overlap save method. So you may be wondering, why do you need different methods for convolving two large series, or to convolve one series with a large series? Whether you can't use the ordinary algorithms which you use for convolving two series. So the catch is that you can, if you convolve these two series Hn and Xn, you require n plus m minus 1. If you convolve this, the total length of, if this is the length of capital N is the length of Hn and capital M is the length of Xn, and if you convolve these two, the total length of the output will be n plus m minus 1, and the total multiplication and addition that happens in convolution also you can determine from this, which is very large. So if you want to reduce it, we can use different methods. And you may wonder, how do you, or why do you require this multiplication and addition to be lessened, or why do you want to reduce the number of multiplication and addition? This is always required because when you implement these kind of algorithms in hardwares, for example in a digital signal processors or in some other hardwares, always you require minimum number of multiplication and addition. So to reduce that, we always go for algorithms which have lesser number of multiplication and addition. For example, you know that we have DFT, discrete Fourier transform, and you know how to compute discrete Fourier transform. If you have a signal xn, you compute it as sigma xn e raised to minus j 2 pi by n into kn. Okay, so k varies from, say, if you have causal signal 0 to infinity, and you find this. But this also take a large multiplication and addition. So you go for some efficient algorithms, and there are efficient algorithms called fast Fourier transform, which is the algorithm used normally implemented in hardware or in simulation softwares like MATLAB, Scilab, Octave, etc. And this FFT, fast Fourier transform, is basically DFT itself, but the algorithm is faster. That's why it is called fast Fourier transform. It is DFT itself. So if you implement it in MATLAB or Scilab, you may be using the functions FFT, because an algorithm which is faster than DFT is used here, or the multiplication and addition are lesser, and the systems run faster also. So this kind of faster algorithms always help in speeding up the process, as well as making the implementation in the processors, whether it is a DSP processor or some other ARM processor or whatever it is, it becomes easier. So these are the two methods that we are going to see today: OverLap add method and OverLap save method. So let us go into details of this. First, let us see what is OverLap add method. Okay, suppose you have a signal h of n. H0 you have value 1, 1 you have value 2, and 2 you have value 2. Okay, suppose this is the signal. Okay, this let it be 3. So this is Hn, and suppose you have an Xn. Xn is another signal. Suppose it is a very large series. Suppose this also 1, and 6 here. 0, 1, 2, 3, 4, 5, 6, 7, 8, like that it goes. Okay. So this is value 2, this value 5, like that it goes. Okay. So in this case, if you want to convolve Hn and Xn, what you can basically do is this Xn you can split into small pieces. So let us call first piece as x0n, which is of duration 3. Let us call this x0n. And then you have exponent starting from here, again 3 numbers, this exponent. And starting from here, you have x2n plus etc. Okay. So basically, xn is x0n plus x1n plus x2n plus etc. up to how many terms you have. Okay, so this is xn, and you know what Hn is. Now suppose you want to do the linear convolution of h of n and x of n. How will you do? You convolve h of n with x of n is basically x0n plus x1n plus etc. So this is same as Hn convolution x0n plus Hn convolution exponent plus etc. Till how many you have. So if you do Hn convolution x0n, what you're going to get is this is of length 3 and this is also of length 3. So if you convolve Hn and x0n, the length of the output will be n plus m minus 1, that is 3 plus 3 minus 1 is 5. So y0n, let us call the convolution of this as y0n, or the final output yn you can write as y0n plus y1n plus y2n plus etc. So this is your final output, and y0n is Hn plus x0n, which is of length 5. So if you try to plot y0n here, suppose you plot y0n here, the y0n will be some value. Suppose this is y0n, or let us plot yn together here. So you'll have y0n here. It will have some value, say, let it be some value 5. This value is 2 at 0, 1, 2. It have these values. Okay. This y0n. Y0n is of length 5. So you'll have 2 more values. 1 value, 2 value. At 3 and 4, you have these values. So this is your y0n. And what about y1n? Y1n will be here. It will be starting from third position. What will be those value? Y1n. Y1n will have values here. It may be some, say, 3. Again, suppose it is 4, 1, yeah. You have 2 more values. Okay. So you have some overlapping here. This y0n, y0n and y1n are overlapping, and these are to be added because yn is basically y0n plus y1n. So these will remain as such in yn, but these values, the brown and the yellow, will get added to get whatever the value of yn is at this region. Similarly, there will be overlapping at this region, etc. And finally, you will get y of n. Now, if you implement this in, say, a digital processor, what you do is you will find the DFT of x0n. You will find the DFT of x0n. You will find the DFT of x1n, etc. So x0n, x1n, x2n, etc. You will find the DFT of this. Okay. Once you find the DFTs, what you will do is you will, instead of linear convolution, what you have done here is linear convolution. First, you will zero pad with n plus m minus 1 value. You will zero pad with n plus m minus 1 value, and then do circular convolution, or the equivalent of that is DFT. First, you will take hn. You will zero pad with the remaining values. Say you have 5 value, so 3 values here. So you will zero pad with at 3 and 4. You will zero pad. So this, you will take DFT of this, which will give capital HK. Similarly, for x0n, you will find x0k after zero padding. For x0, you will take first 3 values, then zero pad it. Okay. X0n is 3 values. You take it, zero pad it with 2 values. Then you find x0k. You multiply x0 and hk and take IDFT. You will get y0n. So this value you will keep here. Then you do it for y1 and y2 and etc. and add them together. Then you are going to get yn, and this can be easily implemented in a computer or in a digital device like DSP processor or some other processor. So by that way, you will get easily y of n. And in this method, the multiplication, addition, and the computational complexity is lower. So that's why you go for this overlap add method. Now we'll do problems from this. Then you will get more clear how the process is going on. Okay, concept will be clear. Now we will see what is overlap save method. In overlap save method, what you do is again you have a signal h of n. Okay, suppose this is h of n, and you have this is a finite series small signal, and h of n is a large infinite series or very large series number. So at 0 you have one value 5, at 1 you have one value 4, at 2 suppose you have 1, 3 you have some value 8, 4, suppose you have 3, 5 you have some value say 8 again, 6 suppose you have 2, like that. This suppose this is an infinite series, and again you are convolving these two. OverLap save method is computationally little better than OverLap had method. So we shall see how this is done. And before that, let us see what happened when you do convolution of three numbers. Suppose you have 1, 3, 2, and suppose you have a signal. Say, let us call a signal as set of n, and suppose it has some value. Say this has some value 2, this has some value 1, and this has some value 3 and another value 4, 0, 1, 2. Sudden is from 0, 1, 2, 3. Okay, suppose this is 0 padded with this. Can you do circular convolution of h of n and z of n? Can you give me the answer? Can you convolve h of n and z of n? H of n is of support 3 and z of n is of support 4. So can you convolve h of n and z of n directly? You can unmute and tell. Don't type anything. I won't be able to see the messages. Okay, I'm not hearing anything. Anyway, am I audible to all of you? Is the video and audio clear? Please give me some feedback.
Yes, sir.
Okay, fine. So h of n, normally if you circularly convolve two series, they need to be of same size. So suppose you do Zn convolution, h of n convolution z of n, h of n convolution z of n, and suppose the size of hn is 3 and size of zn is 4, and suppose you zero pad here some a zero value and do the convolution. Okay, normally if you want to do circular linear convolution of this, what you will do is you can put say zero padding of n plus m minus 1, so that the size become n plus m minus 1 if this size of this and this are n and m respectively. So if this is 3 and this is 4, n plus m minus 1 will be 3 plus 4 minus 1, which is 6. So 3 you will zero pad with two more values, 3 values here, and here you will zero pad with 2 values, so that the total length become 6. Okay, and you will do the circular convolution, and what you are going to get is a linear convolution. But suppose you don't do a zero padding, and if you do a circular convolution with this much values, for example values with this only, suppose you do circular convolution of these two, what you're going to get is you will not have all the values correct, but some of the values will be correct. For example, if you do circular convolution of these two, the last two values will be same as that of the circular convolution. So let us see this using MATLAB. You can use either MATLAB or Scilab or Octave. I have Octave also in this, but Octave sometimes hangs. But Scilab works okay. So today I will show with MATLAB. Suppose you do say, let's take those numbers itself. 132 is 132, and I'll zero pad here. Okay. It's 1320. Now I'll take 2134, 213, and okay, so this is the 213 and 4. Suppose I do circular convolution of this 2. Okay, let us call this as Z and Z. So circular convolution, you can use CCirc, which is the built-in function in MATLAB and Scilab. CCirc, comma A, comma Z, and you can give the window length. Window length is 4, so comma 4 you can give. So let us call this say capital Z, or as a capital Z we'll call it Y. Okay, C unrecognized function. C is convol. C is CONV A, comma Z, comma 4. Let us call it Y. So what you have got is 20, 15, 10, and 15. Okay, by circularly convolution 1320 and 2134. Now, suppose you take the linear convolution. Linear convolution, let us call it as L. So L is con A, comma Z. This is a linear convolution. So you can see that it is 2, 7, 10, 15, 80, 8, and 0. So you can the last two numbers in Y, that is 10 and 15, is there in L. It is the third and fourth one. Similarly, suppose you have the signal A as 2134. So let us call A1 as instead of 2134, I will zero pad two numbers with 0. Okay, instead of I have 1320 as A, and Z I have 2134. So instead of 2134, I will take 0021. So let instead of Z A1, I will take Z1. Z1, let it be 0021. Okay, so if I do the circular convolution now with Z1, you can see that you get 7227. So in the linear convolution, if you see L, so this is L. The last two terms of circular convolution of A Z1, 4 is 27, which is the first two in the L linear convolution, 27. And when you repeated, you know that you got 10 and 15. That is when you take the all the numbers 2, 1, 3, 4. And suppose you take instead of Z in 2, 1, 3, 4, you take 3, 4, 0, 1. You shift it by 2 again. And if you do the shifting by 2, again you will get the next two numbers. So instead of, let's call it Z2, let us take 3, 4 and 0 pad with next two values and do the circular convolution again. Instead of Z1, I'll give Z2. Now you can see that you get 10 and 8, which are the next two values in linear convolution. After you see the linear convolution, it is 2, 7, 10, 15, then 18 and 8. So you see the last two numbers of circular convolution of A and Z2, it is 10 and 8. Sorry, 18 and 8. So that 18 and 8 has also come. So that has completed the linear convolution. So in this way, we can find linear convolution using this circular convolution. For that, what you need to do is first you take, suppose you have Hn Zn like this. So whatever be the size of Zn normally will be very large values. So what you do is you take first three values of Hn, 1, 3, 2, 0, 0 pad after 0 padding. So this is Hn, 1, 3, 2, 0. Then instead of taking Zn as such, you 0 pad first with 0 values, 2 0 values. You 0 pad with first 0 value. Then you take first two numbers 2 and 1. So you take 2 and 1. Okay. You do the circular convolution of this Hn, and let me call this as x0n. It's not x0n. X0n is basically from 0 to this value. So let us call it x0 dash n. So if you circularly convolve this, you'll get to 4 values. Let us call it okay, a dash 0, a dash 1, a dash 2, a dash 3. From these 4 values, which you get after convolving these two, you take these two values. So A2, A3, you can keep it here. Again, you take h of n and you shift this by 2. That means you take this whole window 2, 1, 3, 4. You take 2, 1, 3, 4 window 2, 1, 3, 4. Let us call this x0, x dash, x1n. Now you do the circular convolution of Hn with x dash, x1 dash, and you will get some y of n, or let us call it y1 dash n. Let it be b0 dash. Let us call this as dash to distinguish. So b0 dash, b1 dash, b2 dash, b3 dash. From that, you take class 2 values, b2 dash and b3 dash. Like that, you can, if your series is of length 100, you can do this till it reach 100 values, and you will get all these values. And this is basically the linear convolution of your signal h of n with this very large or infinite series number. And hence you get this. And here you can see that from A0, A1, A2, A3 dash, etc., you take only these two. You are saving these and you are not considering this, or you are rejecting this from each of these. So that's why the name came overlap save. In this overlap, some of them you reject and some of them you save. So this is how you get overlap save method. So from the MATLAB simulation or the Scilab simulations, you will get understand what these things are, and I hope you got the idea of these two methods. So now I stop sharing. Um, I hope you understood what these two methods are for, and what are they? The overlap add method and overlap save method. These are for finding linear convolution, and the linear convolution with efficient manner, computationally efficient, um, better for DSP processor or hardware implementation in a digital device or in a computer, any digital device. And in the first method, you saw that you add the overlap, while in the second method, you reject some of them and save some of them, and it is called overlap save method. So first one is overlap add method, and second one is overlap save method. And in if you compare the multiplication and addition required for normal linear convolution of these finite series and infinite series numbers, the number of multiplication additions are very less compared to um, in the case of so the overlap add and overlap save method. So I hope you got the idea. If you have any doubt or something, you can ask me in Moodle chat, or you can ask now. The video I'll upload in Moodle, upload in YouTube, and give a link in Moodle. You can access that, and you'll have a quiz today based on today's class. So if you have any doubt, please ask. If you have any other concerns or something, you can ask there now. Otherwise, yeah, do you have any? Okay, if it's fine, we you can proceed to the next class. Thank you, all of you. Thank you. Amal, are you there? Amal Krishna? Nandakumar, are you there? Neat?